Okay, class, we're going to do these notes and I'm going to record them because my voice is shot. So this looks like the warm-up we just had, and apparently I didn't put the lines in correctly, so we can adjust them real quick. But this is an example of a proportional situation where x is 0, y is 0. 1 is 3, okay? So that slope should actually be up here. But the point I need for you to take out of this is, what do the two graphs have in common? Slope is the same. What's different? The y-intercept. Okay? 0 in proportional relationships. Okay? Not equal to 0 in non-proportional. Relationships. Okay. This is a good time to talk about this. Today, we're doing explaining proportional and non-proportional situations, and no matter how I do this, it still tells me I'm spelling it wrong, but whatever. The questions are here, okay? Under what situations is a linear relationship proportional? Okay? How is slope different from the constant of proportionality? Those are the two guiding questions for today. The concept here is all about relationships. Okay? All right, so here's something to really think about. This is the thinking, concentrating emoji. Two related quantities are proportional if they have a constant ratio between them. If two related quantities do not have a constant ratio, then they are non-proportional. We're going to write something in here. Constant ratio equals unit rate. That's what we mean by constant ratio is equal to unit rate. Okay? This whole idea of constant ratio has so many different names, it's confusing. All right, so let's look at the first example. The cost of a CD at a record store is $12. Create a table to show the total cost for different numbers of CDs. Is the total cost proportional to the number of CDs purchased? So if one CD is 12, 2 is 24, 3 is 36, and 4 is 48. When you set these up as ratios, are all of these ratios equivalent ratios? Can you see that 12 to 1, 24 to 2? So each, no matter how many CDs I buy, the CDs are $12 per CD. Okay? Divide the total cost for each by the number of CDs to determine the ratio and compare the ratio. So if you simplify all of these, they're all equivalent to 12 over 1. Since the ratios are the same, the total cost is proportional to the number of CDs purchased. Okay? All right, let's look at the next situation, example 2. Okay? The cost to rent a lane at a bowling alley is $9 per hour plus $4 for shoe rental. Create a table to show the total cost for each hour a bowling lane is rented if one person rents shoes. Is the total cost proportional to the number of hours rented? So can somebody raise their hand and tell me, where does this 13 come from? Why is it 13? Connor? Okay, what do you say, Emma? So what's that $4 for? Does the $4 for shoe rental, do I pay that $4 for every hour or no? Just one time, right? It's a one-time thing. So what's the difference between the 13 and the 22? Elena? So if we look at this, doesn't it go up by 9? And here, doesn't it go up by 9? And up by 9, and then there's 1 and 1 and 1. Up here, wasn't it plus 12, plus 12? What's the slope up here? 12. What's the slope here? They both have slope, right? Okay. But when we look at the ratio, comparing the total cost to the number of hours, 13 over 1 is 13, 22 over 2 is 11, 31 over 3 is not 11, 40 over 4 is 10. If these are different, it's not, if they're different, it's not proportional. And all you need to do is look at the first two. 13 and 11, they're different. On this one, 31 divided by 3, there's a decimal to the hundredths place. You don't need to do that to figure out if it's non-proportional. All you need to do is figure out that it's not 11 or it's not 10. If they're different, it's non-proportional. If they're different, they're what, class? Right. Okay. So we have a proportional situation and a non-proportional situation. This is a weird deal. Theoretically, at 0 hours, before he even gets charged for the number of hours he rents the bowling alley, how much does it cost him to bowl? $4, right? We call this the zero rule. We call it the zero rule because it helps us figure out certain things about situations, whether they're proportional or not, and how to write an equation for them. Turn your page. So here's two things. I'm going to stop talking for a minute, pause the video. Talk these two scenarios over, and do you think they're proportional? Okay. A photo developer charges 25 cents per photo developed. Is the total cost proportional to the number of photos developed? Okay, we've talked about it, and we've noticed that in this situation, it was proportional per photo is okay, but no fee. So let's look at the next one. A soccer club has 15 players for every team, with the exception of 2 teams that have 16 players each. Is the number of players proportional to the number of teams? What do you think? No. So y'all take a second and think. And okay, I've heard some good conversation, and really what it boils down to is maybe this. Remember, we talked about proportional situations always have the same unit rate. Can somebody tell me the unit rate in this situation? What is the unit? What is the comparison here? Miguel, what's the comparison? Teams to what? Teams to players, right? So in some circumstances, we have 15 players on a team, but in other circumstances, we have 16 players on a team. By definition, that's non-proportional, right? Okay. All right, let's move on. We're going to graph these situations to identify traits of proportional and non-proportional situations. Okay. A person can burn 8 calories per minute running. Determine whether the number of calories is proportional to the number of minutes. So in 1 minute, how many calories they burn? Two hours, 2 minutes, sorry. 3 minutes? Okay. So can we just graph this like this? Okay, what do we know about if we run 0 minutes, how many calories do we burn? Okay, 0. What do we say about y? So y is equal to 0. Rachel baked 3 cakes in 2 hours, 4 cakes in 3 hours, 5 cakes in 4 hours. Okay, in 2 hours, I baked 3 cakes. Right? This is cakes, hours. Okay, 2 hours, 3 cakes. 3 hours, 4 cakes. 4 hours, 5 cakes, right? Okay, if you drew a line from here to here to here, shouldn't the next line go right there? And wouldn't the next line go right there? So what can we say about y when x is 0? Y is equal to what? 1. Okay? Now, the slope for this one is what? We go back over here. The slope is that it's going up how much every minute? 8. This one goes up how many cakes every minute? Or hour, sorry. 1, that's m because it's slope. 1 cake. It is a slope of 1. Okay. Now, if you counted rise over run, does it look like 1 if you just count the little lines? No, it doesn't. It looks like it's going up by 1/2, but that's just the way it's calibrated, right? It's vast. It's calibrated really different. Okay, so let's go back over here. Write an equation using m for slope, x and y to explain the situation. So if y is 8, our y is 8, our slope is what? 8 times 1, right? So 8 calories per minute times 1 minute gives you a total of 8 calories. 16 calories is 8 calories per minute times 2 minutes, right? You with me? Okay, since every minute x gives you y calories, we write this. Does y equal x? Does 1 equal 8? What did we do to the minutes to make it the total calories? Times 8. So what 8 is m, right? So we call this the y equals mx. We call it the y equals mx. Okay? This is a proportional situation because the ratio of yx is constant for all ordered pairs. Proportional situations vary directly, so we also call them direct variation. When direct variation exists, we can calculate the constant of proportionality. That is also, or the k. The k is a y over x that is constant. It is a constant unit rate. Okay? So proportional situations have a what we call a constant of proportionality, a direct variation. It's called the k. So when we say is a situation proportional, if we say yes, then it has a k. If we say a situation is non-proportional, then it has no constant of proportionality and it has no k. Okay, so y equals mx here. Okay, all right, we're going to move over into here, and I'm going to pause this video because I'm out of time. Okay, here we go. We were talking about the y equals mx is for proportional situations. So let me repeat this. That we call this thing a k when you have a constant of proportionality. That is the k. It's also called direct variation. It's a constant unit rate. That's what it is. It's a constant unit rate. Okay. Now, so from here, let's go and compare and contrast this to non-proportional. So where slope is m, so we have an m, we have an x, we have a y. But do you think we can use the same equation? Let's try it. So if we take, say, m times x, and that gives you y, if we plug in, say, our m is 1, and our hours are 3, is 3, at 3 hours, how many cakes do I have? Are you sure? Look at the graph. At 3 hours, how many cakes do we have? 4. Is 1 times 3 4? No. No. It doesn't work. So it doesn't work unless we consider the y-intercept, the value of y when x is 0. In equations, this, we call this the b. We use b to indicate where we use b to refer to the y-intercept. So we write this equation because this equation considers the y-intercept. Y equals mx plus b. Now let's try it again with mx plus b. Does 4 equal 1 times 3 plus, what's the y-intercept up here? The y-intercept is 1 plus 1. 3 plus 1 equals 4. So this is our y equals mx plus b. This is a non-proportional equation because the y to x ratio is not constant. For all ordered pairs, if the relationship is non-proportional, there is not a direct variation or a constant of proportionality. Not proportional, no direct variation, no constant proportionality. That means no k. There is no k. Okay? Now, finally, we come down to this. Both proportional and non-proportional relationships can be linear and have slope. They are different because we cannot express them in equation form the same way. Okay? I encourage you guys to use your notes. Hopefully this video, in spite of my horrible sounding voice, is going to be helpful. Hopefully on part 2, I adjusted the microphone to where it doesn't sound like I'm yelling. Okay?